Welcome to everyone to this lectures on combinatorics, week 3. In the previous previous 2 weeks, we looked at pigeonhole principle in the first week and several of its applications. And then we went to look at several basic counting techniques in combinatorics that one can use, like the addition rule and the product rule, and some other interesting results related to this. And then we looked at some applications. Now we are going to look at further applications of these basic techniques to develop a little more advanced tools or results that we can use in many situations. And that is what we are going to do in this week's lectures. So we start with a very interesting problem. Okay, so it is the following. So consider the equation summation xi is equal to n, where I ranging from 1 to k. So x1 plus x2 plus etc. xk is equal to n. Now xi's are restricted to be non-negative integers, that they can take value 0, 1, 2, etc. Now given this condition, look at any possible solution to this, right? So any solution to this equation can be described as a k tuple, something like a1, a2, etc., ak, where ai is the value taken by xi, where xi can be, let's say, 0 or 1, 2, etc., right? So if x1 is equal to 5 and x2 is equal to 7, then we will have this tuple starting with 5, 7, etc., where I1 is equal to 5, I2 is equal to 7, right? Such a tuple is called a weak composition of n into k parts. K parts because, we are basically writing n as a sum of k non-negative integers. Okay, so this is called a weak composition. Now, before trying to find out, our ultimate aim is to try to count the number of possible weak compositions here. But before that, let us also look at a slightly different definition, where we allow xi to be strictly greater than only to be strictly greater than 0. That xi cannot be 0. Okay. So if you have equation exactly the same, right, x1 plus x2 plus etc. xk is equal to n, where xi is strictly greater than 0 to be a positive integer, right? Xi's are positive integers. Then again, any solution given by the ordered tuple a1, a2, etc., ak, where ai belonging to n plus is called a composition of n into k parts. So it's not weak composition, it is composition. So maybe at later point of time, it will be clear why it's called weak and the other one is to be not weak, right? But for the time being, let us just take the definitions for granted. Now, can you think of any argument to count this number of possible compositions or number of possible weak compositions? Okay, so I tell you that both of these can be solved by some results that we already looked at. Okay, so with this information, can you think about this and find a solution by your own? So maybe you should spend some time, pause this video, spend some time trying to figure out how to count these two things. Okay, it will be very useful if you spend some time thinking about this instead of looking at the solution that is presented here. Okay, so here it goes. So we will first try to solve the second question, that is to count the number of compositions of n into k parts. Okay, so since we want to make our the lectures, or we want to remember the lectures to be sweet, let us convert this question into a more enjoyable form, right? As follows. Okay, suppose we are given let us say n, which is greater than or equal to k. Let's say ladoos. Okay, so n ladoos, like identical, same kind of ladoos maybe, or Tirupati ladoos maybe, one of the most famous ladoos, tastiest. And they are given, and we want to distribute it to let's say k children. Okay, so if you think that you are children, then maybe you can hope to get some ladoos, right? Now, so we have enough ladoos so that we don't have to be like we don't have to be very selective, right? So we can say that every child is going to get at least one laddu. That I will guarantee. Okay, so everybody will get at least one laddu. Then how many ways you can give the laddus to the K children? That is the question, right? Because even though I said that everybody get at least one, I did not say everybody will get equal number of laddus, right? But at least if you get one, you can be happy. So we will make sure that everybody gets at least one. So now the question is that how many ways we can distribute the laddus. Now one can immediately see that this question is precisely the question of composition, right? Because now you can assume the number of laddus received by each of the k children to be the values taken by xi's, and they sum to n, and then the number of ways to do the distribution is precisely the number of solutions to this previous question of composition of n into k parts, right? Because xi's are to be strictly positive, everybody gets at least one, and it should be integers, so everybody gets at least one. Now, how do you solve this question? Again, think of laddus if it helps, and try to figure out how to do this yourself. If that doesn't help, we go to the next page. Okay, so let us assume that there is a hall where the children are waiting, and then there is a table where all these laddus are kept in a line. Okay, so we have these laddus which are kept in a line, right? So laddu 1, 2. I think I took the wrong tool. Laddus, yeah, 1, 2, 3, etc. Right? All the n possible laddus are there. Okay. Now, this is supposed to be n. So all possible laddus are there. Now they are kept in a straight line. Okay. Now we want to distribute the laddus to the children, right? So how do you do? Okay, we will say that okay, children queue up, right? So okay, stand in a line. So the child number 1, number 2, etc. stands in one line, right? So they stand in a line, and then we will say that okay, see the first child can start at the beginning, right? The first person starts at the beginning here, or maybe I will even use this. So start here, right? Because we want to use all the laddus, right? So we will say that okay, you start at this, at the very beginning, the first guy in the queue. Then you start taking some laddus, right? And once you take some laddus, I don't know, 1 or 2 or something, right? Some number, whatever, maybe 5, depending on the person who is standing there. Okay, now go, right? So once he has taken some number of laddus, we will say okay, now the next guy in the queue comes. Okay? So the C2 will start at this place, right? So the child number 2 starts at the position which is after the first guy is asked to leave. Again, he will take some laddus, and then suddenly the person who controls the queue says that okay, you leave, next guy. So this way, each child will be allowed to go and take something. Now, since everybody gets, we need to make sure that the last child gets at least one. So he should start before the end, and then he should be allowed to take whatever is remaining, right? Whatever remains should be given to the last child, so that all the n laddus are distributed to the k children. So this way we want to make sure that everybody gets at least one laddu. Now, how many ways this can be done? This is easy, because what we have is that we have to decide where each of the children starts, right? Now the first person doesn't have a choice, right? So we don't have to look at that, because he always starts at the beginning, right? So therefore we need to only decide the remaining k minus 1 children, right? 2 to tk, where they are going to start. Now they can only start at some point in between, like in these laddus, right? So there is n laddus which are kept here. Let's say 1, 2, 3, etc. N laddus are kept here, and therefore now the positions where the children can start are in between these laddus, right? So if there are n laddus in a line, how many gaps are there in between? So there are exactly n minus 1 gaps in between. So out of these n minus 1 gaps, we need to decide which are the positions where the k minus 1 children are going to start taking the laddus. So once we know that, we know the number of ways you can do that situation. And how many are there? Well, since there are n minus 1 gaps available, and we need to select k minus 1 of these gaps where the children can start, n minus 1 choose k minus 1 possible choices are there, right? So these are the number of available choices, and each choice correspond to a composition, and every composition corresponds to one of these choices, and therefore this is a one-to-one correspondence, and we get that the number of possible compositions of n into k parts is n minus 1 choose k minus 1, or is equal to n minus 1 choose k minus 1, right? Yeah. So this is the number of compositions of n into k parts. Okay. So is that clear? Now, what we are going to do is now to look at the first question, right? What was the first question? We wanted to look at the weak composition, right? Weak compositions are the solutions xi greater than or equal to 0 instead of xi strictly greater than 0. So we found out that the number of compositions is precisely the ways of distributing sweets to children, right? So we had a great time solving this. Now we want to solve the other question, right? So here is a theorem which says that the number of non-negative integer solutions to the equation x1 plus x2 plus etc plus xk is equal to n is given by n plus k minus 1 choose n. Okay. Now, how do we prove this, right? Now, since we already solved a question of composition using sweets, why don't we try the same thing, right? Maybe we can still work with sweets. So let us start by assuming that let x1 to xk be the number of laddus children got when n laddus were distributed to them, right? See, n laddus. So here also we are doing the same thing, right? We have n laddus. We are going to distribute them to children, but now the person standing at the queue may not be fair, right? He will say that, okay, some children who comes, I don't like you, right? So you don't get anything, right? This is possible, right? So there is somebody standing there. You will say, okay, first guy come, okay, you take something. Second guy take something. Third guy, no, you go, you don't get anything, right? Then fourth guy. So this way, we can make some of the exercise to be zero, right? So when the distributor is unfair, then this can happen. Now, can you convert this to the previously solved problems? Any one of the previously solved problems or the previously solved problem just before, right? If you can convert it to a previously solved question, then that is the best thing to do in mathematics, right? Because you reduce the problem to an already solved problem. So if you can do that, then we are done, right? If you can convert into a previously solved problem, then that is it. So how do you convert it to a previously solved question? So again, I want you to think about how to convert this to the previous question, right? So can you convert the unfair distribution to a fair distribution question? If you can do that, then that is good. So this is quite easy actually, right? Because we want to distribute n sweets to k children, so that everybody gets. Some kids may not get anything, but now we want to convert into the question that everybody gets at least one. Now, how do you make sure that everybody gets at least one when some of them can clearly be zero, right? So what you do is that you assume that from each children before the distribution, right? For each children, we will go to the child and say that, okay, we are going to distribute some sweets, but now since we don't have enough, can you please give us one laddu each, right? So from every child you borrow one laddu, right? So you take one laddu from each of the children. Now keep it with you. So now you have k extra laddus, right? So you take the k extra laddus and then put that also in the table. Now you again send the children back to the queue, right? Now whenever a child comes, he will definitely get at least one, because he gave one laddu to the distributor. Now no, this guy cannot say that, okay, you don't get anything, because he will say that, okay, I already gave you one laddu, I should get at least that one back. Now what does this mean? This means that everybody gets at least one, which means that you get xi strictly greater than 0. But now for every solution to the weak composition, or the solution to the distribution where xi can be greater than or equal to 0, we have a solution where xi is greater than or equal to 1, or xi greater than strictly greater than 0, right? Because you just add 1 to each of the xi's, and on the right hand side you have, instead of n, you have n plus k, because we started with k additionally too, right? So therefore, distributing n laddus to k children, where everybody gets greater than or equal to 0 laddus, is equivalent to saying that distributing n plus k sweets to the same k children, where everybody gets at least 1. Because whenever you have a solution to at least 1, you remove 1 from each of them, you have k less laddus, right? N plus k minus k, which is n laddus, and some of them can become 0 now, because xi was 1, it will become 0, right? So there is a one-to-one correspondence between the solutions, so they should be the same. So that is it. So we have already converted it, right? So we said that, okay, solutions to xi plus etc. xk is equal to n, xi greater than or equal to 0, are in 1-to-1 correspondence, right, with the solutions x1 plus etc. xk is equal to n plus k, where xi is greater than or equal to 1, or xi strictly greater than 0, right? Xi greater than or equal to 1. And we know how to do this because we just did in the previous exam, right? It's basically whatever was that number n plus k minus 1, choose k minus 1, right? Which is equal to n plus k minus 1, choose n also, right? By the property of binomial coefficients, right? So therefore, this is what we wanted to prove. N plus k minus 1, choose n. So we already have the solution, right? N plus k minus 1, choose n. So this is one way we can prove this. Now let me give you another proof, okay, to the second, the first question, weak composition. So the proof 2 is also quite nice. This is by using another result, right? So what we do is that we observe that the number of ways to distribute the laddus to the kids can be made as follows. Okay, so you keep your n laddus here. Okay, so the laddus are here, this one, this one, this one, etc. All the n laddus are kept here. Now once these laddus are kept, what we are going to do is that we separate the laddus by putting some markers or sticks in between them. Okay, so here are the sticks, right, which separates the laddus. When of course these the sticks can be together so that there is no laddu in between. That is also possible, right? So we keep some bars or k minus 1 sticks in between to separate the laddus. Now the sticks, once they are kept, this decides the composition or the distribution of the laddus, because you will say that okay, the first child can take all the laddus till the first stick. If the first stick is in the beginning, then that guy does not get anything, right? So xi can be 0, x1 can be 0, right? Similarly, after the first stick, so the laddu is taken, the first stick is removed, and then say that again, second child now go take the laddus till the first stick again. I mean, the second stick, which is the remaining, set the first or the next stick, yeah, right, till the next stick. So from this to this. Again, the third child goes and take the laddus till the third stick. So this way, the k minus 1 children take, and the remaining laddus, if there are any, because if the stick is at the last end, then there is nothing remaining. So which means that the last guy also may not get anything, right? So you can take, right? So this is basically, you have the laddus and sticks, and then you are arranged. You put the so as I told you, some of the sticks can be like this, right? You can have 2 sticks like this, so that after the first guy, the second guy does not get anything, right? Or maybe there is something like this, the last 2 guys does not get anything, right? So this is possible. But yeah, now all we have to do is to find the number of possible arrangements of the laddus and sticks. But this we already know, right? Because we already said that, right? If you have, so laddus are one type, right? So there is n objects of type laddu, and then k minus 1 objects of type stick, right? So we want to arrange the laddus and sticks in any possible way, right? So how many possible arrangements are there? By the multinomial theorem that we studied, right? If there is n1 objects of type 1 and n2 objects of type 2, the number of permutations of them is basically n factorial by n1 factorial into n2 factorial. So therefore we have n laddus and k minus 1 sticks. So n plus k minus 1 total objects are there, out of which n of them are of one type and k minus 1 of them are of different type. So therefore n plus k minus 1 factorial divided by n factorial into k minus 1 factorial, which is precisely n plus k minus 1 choose k minus 1 or n plus k minus 1 choose n, whichever you want, right? So therefore by the multinomial theorem, we immediately get that this count or the number of possible arrangements or the number of weak compositions is equal to n plus k minus 1 choose k minus 1. So that is it. So we have another proof. Okay. Now here are some homework questions for you. First is that you count the number of compositions of n if any number of parts are allowed. Okay. So what do I mean by that? So earlier we said that we have a fixed number of k parts are there, right? So we counted for precisely k. Now you want to find out for arbitrary number of, where k is arbitrary, right? It can be 1, it can be 2, it can be 3, etc., right? Now, can you find a close formula for this, right? Now, close formula is a formula without the summation sign. So I don't want, because you can always write, summation k is equal to 1 to blah, 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 n plus k minus 1 choose, what is that? N minus 1 choose k minus 1 or something like that, right? So this is very easy to write because we already know for any fixed k, you can always write a summation formula like this. But we don't want that summation form. We want the closed form where you find the formula without using the summation. Right? So you basically do the summation and give me the formula, or find another way to find it directly. So whichever way you want, you can do it. And the second part of the question is that what difference it makes if we allow the composition to be weak composition. Okay, so in the first part we are saying that count the number of compositions of n, you find the closed formula. Now the second question is that what difference makes to this closed formula if we allow the weak composition instead of the composition.